Hi children, please do this practice problem. Wow, great job using 1/2 mv squared equals k, the kinetic energy. Hazel, have you ever played golf? No, Mr. Lamb, I'm a baby. Oh right, I forgot. But you've seen a golf ball, right? Yeah. So you think a golf ball is elastic? No, Mr. Lamb, it's hard, it's like a rock. It hits you in the head, you're gonna say ouch. Okay, let's watch this video. One more time. Great. This is a real video produced by the United States Golf Association, but it's with a real golf ball, and it's really fast. The ball is going 150 miles an hour, and the camera is recording 40,000 frames per second. So it might not look exactly like what you've seen, but this is what happens when a golf ball hits a solid wall. It is a little bit elastic. When you guys hear the word elastic, most people think of the material. They say, "Oh, my hairband is made of elastic. Oh, my underwear has like an elastic waist." That's not what elastic means. Elastic means that when an object is deformed, when it changes shape, it gets restored to original shape. It restores its original shape. The opposite of elastic is another word that's similar. It's plastic. Everyone thinks, oh, plastic is a material made of dead dinosaurs. Plastic doesn't mean that. Plastic means this object, if it's deformed permanently. When you make a dent in something plastic, it'll stay dented. Like Play-Doh. If you punch Play-Doh, you'll see a big fist print in the Play-Doh. Play-Doh is plastic. This can help us explain why things bounce. I'll use the ground, for example, because usually it bounces on the ground, even though the video didn't show that. The ball came down and hit the ground at speed v. It hits the ground, it gets a little squished. This happened last lesson too also. And then it bounces back up at another speed. Let's say it was the same speed. Speed v. Hypothetically, maybe, possibly. Could happen. It needs to be squished based on something we discussed 2 lessons ago. How come the ball must be squished in order to bounce nicely? What happened? Why does it need to get elastically squished? To be deformed, but not permanently, to be deformed and then restored to its original size and shape. What was our lesson about 2 lessons ago? Work. And what's the formula? W equals FD. Yes. Does the floor do work on the ball? Yeah. There's an upward force. It's technically a normal force from the floor on the ball. But that force needs to do work. So that's why the ball gets displaced. Basically, the ball would go into the floor, but there's some displacement. When the floor applies a force on the bottom of the ball, it displaces the bottom of the ball inward, to be flat. While doing that, it does work. And to remember, it's negative work when it stops the ball. The ball has kinetic energy, and then right here, at this instant of time, it's not moving. So it went from K to 0, it lost energy. There must have been negative work, and that's also true because the force was upward while the ball was still moving down. It was displaced downward. Then, as the ball bounces up, the reverse happens. The force is upward, the ball is displaced upward, it goes from 0K to positive K. Positive work is done on the ball by the floor. So that's the review of work. So this happened because the ball was elastic. It restored to its original shape. If this was clay or something that was plastic, it would hit the floor, it would get deformed. End of the problem, we'll just stop there. So elastic things bounce because they're elastic, because they restore to their shape. And as they are restored to their shape, the floor does work on them and gives them kinetic energy, and they get launched upward. A side note: this actually doesn't really show up in the AP, but this is an important idea. Perfectly elastic. Usually, there's called a perfectly elastic collision. Don't confuse perfectly elastic with elastic. Elastic means the object goes back to its normal shape. A collision in physics that's perfectly elastic means the ball, in this example, will bounce up with the exact same speed v that it hit the ground with. In real life, that's not possible for a ball, because if it did, it would bounce forever. It'll always, in real life, bounce up with a little bit less speed. But in an ideal physics scenario, the exact speed the ball hits the ground with is the exact speed the ball leaves the ground with. Another way of saying that, K equals K naught. No kinetic energy is lost. If it's the same mass and same speed v, 1/2 mv squared equals 1/2 mv naught squared. So this is a little bit more common, but it's equivalent. The definition of perfectly elastic collision is a collision where no kinetic energy is lost. Okay, so that's all we have to talk about for energy for today. We're going to go on to a different topic, something that is really a forces topic, but it gets thrown into this unit for a reason. So it still refers to elastic objects. The most basic elastic object is a spring, a big metal coil, like a slinky kind of thing, a spring. But this applies to any sort of elastic object, like a rubber ball, a rubber band, a golf ball, what's it bounce, like a sponge cake? I don't know. Anything that could bounce, or anything that's elastic. Not perfectly elastic collisions, elastic. So here's the idea. If you have a spring, it has a normal length. You can call it the uncompressed length or the unstretched length also. Then you apply a force on it. Let's say I apply the force this way to stretch it. You can also apply the force this way to compress it, but It doesn't matter. Oops. If you apply a force to the right, the spring gets a little stretched. It was length L, then the end was displaced. So now it's length L plus D. D for displacement. What will the spring do to, let's say my hand is pulling it, or maybe there's like a ball on the end? The spring will pull back. You can call this force Fs for spring force. Fr is also common for restoring force. I'll just go with spring for now. What does the spring force depend on? If I pull the spring and stretch it, what does the force inside the spring pulling back depend on? What variables? Tell me right now. A lot of people will say it depends on the force F you pull with. Kind of. It's equal to that. Usually, it's equal to that if the end of the spring isn't accelerating, then they will add up to 0. Kind of like normal force and gravitational force for like a baby in my hand. Yeah, that's true. But what else could it be? Yes, Daisy? D, right here. D, D, D. Yes, D for Daisy. Good job. It depends on D. The farther you stretch the spring, the more it pulls back. And same is true for compression. The more you compress the spring, the more it pushes back. It depends on D. Good. Oh gosh, I'm falling. Okay. What else does it depend on? You guys ever look inside a car at the suspension? Probably not, but pretend you did. A car suspension usually has big springs. Yeah, you see the spring right here? The spring? What about, you guys ever take your pens apart when you're bored in class? In classes that aren't physics, obviously. There's a little spring inside that. Looks like that. Are those springs the same? If I stretch both those springs the same displacement d, let's say I stretch both those springs 1 centimeter, will they have the same force inside them? No. One spring. Well, which spring will have more spring force or restoring force? If I stretch them both 1 centimeter, which spring will give me a greater Fs? Force of elasticity pulling it back to its normal size. Good job, yeah. A very stiff, strong spring, like in a car suspension, is harder to stretch. It takes more force to be displaced. If it is displaced, there's more restoring force. So there's a constant for every spring. Super simple, it's called the spring constant. It's the force restoring that spring to its original length at S divided by d, the change in length. So Fs equals kd, or k equals Fs over d. This is known as Hooke's law. Same Hooke that discovered cells, but who cares about that? So, K, Hooke's law, spring constant, amazing. Physics. Yes. One little subtlety that I like to add. Yeah. Minus. Why a minus? Because if I stretch my spring to the right, the restoring force on this end is to the left. If I take this end and put it to the left and compress the spring, the spring will push back to the right. So Fs is a vector. It's always opposite the displacement, or the change in length of the spring. You'll commonly see this as Fs equals Kx also, but I like to make it d and remember it's a vector. Sometimes it's good to give a vector a little hat too. Cool, great job. So that's pretty much it for this lesson. When you understand elasticity, plasticity, which are not too important, just the definition, perfect elasticity is when there's a collision or something and there's no energy lost. The objects go right back to their original size and shape. That's because they're elastic. But the objects don't lose any kinetic energy. That's because it was a perfectly elastic collision. So basically, you could write it as K equals K naught, K1 equals K2, Ki equals Kf, and then you could solve that way. Cook's law we'll come back to tomorrow. Tomorrow? Yeah, probably tomorrow as well. And that's good. And it's also on a green sheet, so don't worry about that. There's something about restitution in the practice problems, but that's not super important. It says in the problem what it is. It's the ratio of speed. So real fast, you'll see the spin later. This is not on the AP. If it's perfectly elastic, a ball that falls on its ground at 5 meters per second will bounce up, in theory, at 5 meters per second. In real life, that probably won't happen with a ball, because a ball that bounces off the ground with the same speed, light and width, would in theory bounce forever. So that probably won't happen. If it bounces up at 3 meters per second, the coefficient of restitution will be this over this. 3 meters per second or 5 meters per second, cancels out 0.6. Doesn't show up on the AP, but it's cool to know. Yeah, and again, in real life, a rubber ball wouldn't bounce like this, but there are real things in physics that do bounce perfectly elastically. They're just not that common in your normal life. Okay, bye.